friends, this is Priyanka. Today we are going to solve a problem on given mechanism. In this video, we are going to draw space diagram, velocity diagram, Coriolis component of acceleration and acceleration diagram. We are going to learn how to draw the Coriolis component of acceleration from the velocity diagram. First, I will read what is the given problem. The driving crank AB of the quick return mechanism as shown in diagram revolves at uniform speed 200 rpm. Find the velocity and acceleration of the toolbox R in the position shown. When the crank makes an angle of 60 degree with vertical line of center PM, what is the acceleration of sliding of the block B along the slotted lever PQ? So this was the given question. Let us first draw the space diagram with some suitable scale. So here we will consider the scale 1:1/2. So first we will draw the fixed link PA. So as per scale we have to take this distance 10 cm and then at point A draw one angle of 60 degree with vertical line and from that draw the crank. So crank AB we have to take distance 37.5 mm. So in this way this point B is getting fixed. Now it is given that the slotted bar PQ, that means this bar PQ is having slot along which the slider at point B is getting reciprocating. So here we have to draw the link PQ in such a way that the link PQ is passing through the point B and its length is given, that is 375 mm. So as per scale we have to take 187.5 mm and we have to fix point Q. Now from this point A we have to take one vertical distance, that is the motion at point R, that is the at R there is the ramp R and here there is the motion along the horizontal line. So for this horizontal line the vertical distance from point A is given, that is 115 mm. So as per scale we have to plot here distance 57.5 mm and draw one horizontal line. Now from point Q the distance R is given. So this distance QR is 500 mm. So as per scale we have to take this whole distance 250 mm and mark here one point on this horizontal line, and this point is nothing but the R, and at which there is the ram R which is having the reciprocating motion. Now we will observe how this mechanism works. So here the fixed link PA, point A is also fixed and about point A there is the crank which is having rotating motion. And at the end of this point B there is the slider and which is having the reciprocating motion along this slotted bar PQ. And at point P this bar PQ is having rotating motion, that is through some angle theta. And at point Q there is the link QR and at this point R there is again ramp is getting connected which is having the reciprocating motion along the horizontal line. So why here the Coriolis component of acceleration is getting calculated? So when there is the slider is having reciprocating motion along a bar or along a slotted bar and that bar is having rotary motion about some particular point, then we are going to calculate the Coriolis component of acceleration. So for this calculation we require here the linear velocity V along this slotted bar PQ for this slider, as well as we require the angular velocity omega for this bar PQ about this center P. So when this V and omega is getting calculated, then from these two values we can calculate the Coriolis component of acceleration. Now we will first calculate what is the linear velocity for this crank AB, because here the rotating speed is given for this NBA, that is the rotational speed of B with respect to A, 200 rpm. So from that we can calculate the omega, that is 2 pi n by 60 which is equal to 20.95 rad per second. So from that we can calculate the linear velocity VBA which is equal to VB which is equal to omega BA into AB. So 20.95 into AB that we have to take in meter, that is 0.075 which is equal to 1.57 meter per second. This is the linear velocity for this crank. So this is about the magnitude, but what about the direction? So we know that this linear velocity is in the perpendicular direction to the link. So again we have to show that, but in which direction we have to show arrow. So if we observe the motion of this crank is given in the clockwise direction. So I will draw here one perpendicular line with the help of protractor. These two edges are perpendicular to each other. So I will align one edge with this link AB, and from the other edge I will draw here one perpendicular line. So here this arrow indicates us the velocity of B with respect to A, that is VBA, and the direction is shown in the same direction of the rotational motion. Now we will take some suitable scale and we will first draw the velocity diagram. Now we will move to draw the velocity diagram with scale 1 meter per second is equal to 10 centimeter. But before that we will consider here the point B dash on this link PQ which is coincident point with B. So we can say that B is on crank AB and B dash is on link PQ, and which is the coincident point. Now we will move to draw the velocity for this B with respect to A. So direction is already drawn, and as per this scale, the scale we have to take 15.7 centimeter. So if we observe the space diagram, 2 points are fixed, that is point P and point A. So first I will locate this fixed point A and P, and from this point fixed point, that is A, I will draw here one velocity in this same direction. So we have to transfer this line from the space diagram to the velocity diagram, and scale we have to take 15.7 centimeter. So here the point B is located. So this vector A to B indicates the velocity of B with respect to A, but point A is fixed, so we can say only VB. Now if we observe at point B there is the slider, and this slider is having reciprocating motion along this slotted bar PQ, and which is having coincident point B dash. So we will first plot the velocity of B with respect to B dash. So how to plot? So there is the reciprocating motion along the bar PQ. So how to transfer this reciprocating motion from space diagram to velocity diagram? So we know that we have to transfer, that is the motion as it is, that is along this line we have to motion. So we have to draw the line parallel to PQ but passing through this point B, because this is the reciprocating motion of slider. So I will draw here one line. So for this reciprocating motion I will use red marker. So transfer this motion. So from B there is one line, but we don't know where is the exact location of this point B dash. Now again if we observe, there is the link P to B dash, because B dash is on link PQ. So again we will draw one velocity line for this link P to B dash. So we know that it is in the perpendicular direction to the link PB dash. So again with the help of protractor we have to draw one perpendicular line. So align one edge with this link PB dash, and from the other edge draw here one line. So this is the perpendicular line. So along this line we have to draw one velocity line. So one point is P and another point is B dash. So point P is already located. So we have to draw this velocity line parallel to this construction line but passing through P. So we have to take the exact direction. So here the point of intersection is nothing but the point B dash. Now we know that where is the location of point Q. So it is the extended line of PB dash. So we have to extend this PB dash, and here somewhere on this there is the location of point Q. So I will draw here, or I will locate here the ratio from this diagram PB dash divided by B dash Q. This is from the space diagram, which is equal to, here from the velocity diagram we have to take the same ratio, that is PB dash small p dash divided by B dash Q. So if we observe, this PB dash is known and this distance is also known, and only we have to find out the B dash Q. Now here we will locate, or we will show the arrow. So here the initial point is P and final point is B dash, because the point P is fixed. So how I can say that this vector P to B dash is the velocity of B dash with respect to P. So I can say only VB dash. And here we will consider the initial point is B dash and final point is P. So we will show the arrow in the downward direction. So I will say that here is the arrow. Now how I can define this vector B dash to be, because here the initial point B dash and final point is B. So I can say that velocity of B with respect to B dash. So suppose that arrow is in upward direction, then how we can define this? So velocity of B dash, that is VB dash B with respect to B. But here we have taken this arrow in the downward direction. So we can say that the initial point is B dash. Initial point B dash. And final point B. Now it is very important to locate the direction for Coriolis component of acceleration, and that's why here we have to clear that we have to take arrow in the downward direction or upward direction. We can select any one direction. Distance of PB dash and B dash Q is not directly given in the question. So we have to measure this distance in the space diagram. So if we measure P to B dash, its length is 12.5 cm in space diagram. But here scale is 1:2. So we have to multiply it with 2. Then it will become, which is equal to 250 mm. And B dash Q, which is equal to 6.25 cm. So as per scale 1:2, we have to multiply here with 2, and which is equal to 125 mm. So we have to take this distance as well as what is the distance in between P to B dash in the velocity diagram, that is here 11.5 cm. So we can calculate here B dash Q. So here millimeter is getting cancelled. So B dash Q having calculation 5.75 and unit is centimeter. So we have to plot this point, that is after B dash we have to take this 5.75 centimeter and we will plot here the point Q. Now if we observe, this point Q is attached with this link QR. So again we will draw the velocity for this link QR. It is in the perpendicular direction. So I will take here one perpendicular line to this link QR. So I will align one edge with this link QR, and from the other edge I will draw here one perpendicular line. So now take the line parallel to this construction line passing through the point Q. So I will take here now exact location of this point of R is unknown. Now if we observe at this point R, there is the ramp which is having the motion along this horizontal line, and which is the reciprocating motion. So how to show this motion? So we know that this horizontal motion is with respect to fixed point. So we have to draw the horizontal line passing through the fixed point. So I will draw here one line, or we can say horizontal line passing through this point A and P. And here is the point of intersection, and this point of intersection is nothing but the point R. So if we observe, this vector AR, or we can say PR, indicates the horizontal motion for this ram R. So if I show the arrow is from fixed point towards point R. So it will indicate the velocity of R with respect to point P or point A. So simply we can say VR. Now in between this point Q and R, Q is the initial point and R is the final point. So we can say that we have to show arrow also, and we will say that here velocity of R with respect to Q. Now we will show this velocity in the space diagram. So if we observe here, the velocity at point B is already shown. Then this velocity for VB dash. So we have to show with respect to P. So here along this perpendicular line there is the velocity and the arrow is shown towards the right hand side. So I will show that, and this is the VB dash. Then here for this link of QR, the velocity is along this perpendicular line. So I will draw here one line and the arrow is in the upward direction, and we can say VRQ. And then the velocity of ram R is towards the right hand side direction. So we can say here VR. Now we will move for the calculation part. So from the velocity diagram, we have to find out the velocity of toolbox at point R. So here is the reciprocating motion along a horizontal line. So this motion is indicated by the vector A to R. So we have to measure the length of this vector, and which is equal to 16 centimeter. So as per scale, 1 meter per second is equal to 10 centimeter. So when there is the 16 centimeter, so here is the question mark. So we will make here cross multiplication, that is 16 into 1, which is equal to 10 into unknown term x. So x is equal to 16 by 10, which is equal to 1.6 meter per second. Now we will find out what is the velocity of B with respect to B dash. So here I have indicated that velocity of B with respect to B dash. So for that we have to measure vector B dash to B or B to B dash. So it is having length 11 centimeters. So as per scale, 11 by 10, that is 1.1 meter per second. Then velocity of B dash with respect to P. So for that we have to measure this vector P to B dash. So if we measure this, we will get 12 centimeter length, and which is equal to 1.2 meter per second. Then the velocity of R with respect to Q. So for that we have to measure the vector QR, and it is 5 centimeters, so which is equal to 0.5 meter per second. Then the velocity of Q with respect to P. So for that we have to measure the vector this PQ. So length PQ is 18 centimeter, and which is equal to 1.8 meter per second. Now we know that to calculate the Coriolis component of acceleration, we require the velocity of this point B with respect to B dash. So we have already calculated. So here is, and we have to also calculate what is the angular velocity for this Q with respect to P. So for that we require the velocity of Q with respect to P divided by length of this bar PQ. So we will calculate it. So 1.8 divided by 0.375, which is equal to 4.8 rad per second. So this is the magnitude. But what about the direction? Now if we observe, the point P is the fixed point, and here the velocity for this VQP is shown in this direction, that is towards the right hand side. So with the help of compass we will decide the direction. So we will take P as a center because P is the fixed point, and move the compass in the direction of velocity. So if I move the compass, here is the direction. So this is the clockwise direction about P. So we can say that here the clockwise direction about P. So here is the answer. So now with the help of this velocity of B with respect to B dash and the value of this omega, we will find out how to decide the direction of this Coriolis component of acceleration. So now we will plot this. So for that we have to plot this link PQ. So we have to take the line parallel to this link PQ, and on that we have to take the distance, that is the point B, in distance in between P to B dash, we have to plot as it is and then draw here one slider. So point B is on the crank AB and B dash is the coincident point. Now if we observe what is the direction of velocity of VBB dash. So VBB dash, we have shown here the direction towards the downwards side. So I will show here. So I will show with the help of the black marker. And this is nothing but VBB dash. And now we have to show the direction of omega. So omega is having clockwise about P. So I will show here, this is the clockwise direction about P. So from that omega QP. Now from these two directions, that is the velocity and angular velocity, we have to find out where is the direction for this Coriolis component of acceleration. So with the help of compass, we will find out that. Now here the direction of velocity is from point Q towards point P because it is in the downward direction. So here we have to take Q as a center and move the compass in the clockwise direction. Why? Because our rotation is in the clockwise direction. So if I take Q as a center and move the compass in the clockwise direction, so I will show here, this is the direction, that is the clockwise direction. That means the arrow is moving from the right hand side towards the left hand side. So here also the Coriolis component of acceleration, we have to show the direction is towards the left hand direction. So we know that this component of acceleration is perpendicular to this link PQ and passing through this point B. So how to show that? So with the help of the protractor, I have to first align one edge with this bar PQ and we have to draw one perpendicular line passing through this point B. So this is nothing but the Coriolis component of acceleration, that is AC. Now what we indicate? So we have to take the same letters as we have used in velocity, that is B to B dash. Now we will calculate the values of acceleration. So here the linear velocities are getting calculated. So from these linear velocities we are going to calculate the radial component of acceleration, as well as here the value of omega and value of velocity of B with respect to B dash is getting calculated. So from that also we can calculate the magnitude of Coriolis component of acceleration. So now if we observe here, the crank AB is rotating at the constant speed. So in this question, angular acceleration alpha is not given, so we will consider this crank AB rotating at constant speed. So here the tangential component of acceleration will become 0, and that is why the radial component of acceleration for this crank AB will become the total acceleration. So this A raised to R BA, we will consider this as the total acceleration of B with respect to A. So A is the fixed point, so simply we will say AB. So how to calculate it? So for that we have to take the velocity square. So what is the velocity for this AB? Divided by length of the link. So here velocity 1.57 square divided by AB 0.057. So which is equal to 32.86 meter per second square. Then we will move for the next, that is the Coriolis component of acceleration for B to B dash. So here we have to take what is the formula, that is 2 omega V, that is 2 multiplied by this omega QP multiplied by VBB dash. So 2 into this VBB dash is 1.1 into omega is 4.8. So from that it is 10.56 meter per second square. Then again radial component of the link RQ. So here is the link RQ. So for that we will take the linear velocity square, that is 0.5 square divided by length of the link. So length of the link we have to take in meter, that is 0.5, which is equal to 0.5 meter per second square. Now next, radial component of B dash P. So this radial component of B dash P is again linear velocity of this velocity square of this b dash p, that is 1.2 square divided by b dash p, that is the length b dash p. So we have already measured with the help of scale and it is 250 millimeter. So 0.25 meter, so which is equal to 5.76 meter per second square. So from these values of the radial component of acceleration and Coriolis component of acceleration, we are going to draw the acceleration diagram. Now we will move to draw the acceleration diagram as per scale. 1 meter per second square is equal to 1 centimeter. So here we will locate the point, that is the fixed point P and A, as a P dash and A dash. We will take first the radial component of acceleration for this crank AB, and which is nothing but the total acceleration at point B. So we know that the radial component is parallel to the link AB and the direction is towards the center. So if I show this direction, that is direction is from point B towards point A. So we have to draw one line parallel to this link AB and in the same direction. So here is the line. And as per the scale, we have to take here 32.8 centimeter, and this is the final point. So this is the total acceleration. So I have shown with the help of black marker, and which is the, we will give here the vector A dash B dash as the total acceleration A at point B. Now if we observe at point B, there is the coincident point B dash. And there is the Coriolis component of acceleration, and which we have calculated as 10.56 meter per second square. So this is the direction that I have shown for the Coriolis component of acceleration of B dash. So in this, what is the initial point and what is the final point? That is the Coriolis component of acceleration of B with respect to B dash. That is, if we observe, or we will take the reference for this velocity diagram. So arrow is shown in the downward direction. So initial point is B dash and final point is B. So we have to write that initial point B dash, final point B. So in the acceleration diagram, this B is located as B dash, and this B dash we will consider it, or we will locate it as a B double dash. Now we have to draw this line. So direction is in the same, that is shown towards the left hand side. But here B dash, so this B dash, that is nothing but B, and this is the final point. So we have to draw arrow in such a way that the final point will be indicated towards the end of this arrow. So I will take here the line parallel to this Coriolis component of acceleration, and I will draw here one line. And what is the magnitude? So magnitude is also getting calculated, that is 10.5 centimeter, and arrow is towards the B dash because B is the final point. So this is the Coriolis component of acceleration. So I will say AC B dash, and here we will give here as a point X. Now we know that the radial component of acceleration and this Coriolis component of acceleration are perpendicular to each other. So I will draw one perpendicular line with the help of protractor. So here I will align one edge with this B dash X, and from the other edge draw one perpendicular line. So the exact magnitude is not known, so I will show here only, or I will extend this line. Now again, if we observe, this B dash is point on the link PQ. So if I take the radial component of B dash P, which we have already calculated, then which is having the 5.76 meter per second square magnitude, and which is equal to 5.76 centimeter, we have to take the distance. So we know that this radial component is along this, or is parallel to the link PQ, because B dash is the point on the link PQ, and where the direction should be shown. So direction is towards the center. So in this vector P to B dash, P is the center, P is the fixed point also, and P is the center, and that we have located here, that is already located. So from this point P dash, I will draw one line parallel to this PQ, and scale we have to take here as a 5 5.76, that is approximately 5.7 centimeter. So this is the vector, that is initial point is P dash, and what is the final point? So I will say y, because this is the component, this is not the total acceleration. So I will say here a raised to r b dash p. Now again we will move for the tangential component of b dash p. So we know that it is in the perpendicular direction to this line. So I will draw here one line which is in the perpendicular direction. So this vector from y we will extend here, and this point of intersection is nothing but b double dash. So what this vector y to b double dash indicates? So it will indicate the tangential component of b dash p. And what this vector x to b double dash indicates? Because Coriolis component of acceleration and radial component of acceleration are perpendicular to each other. So this is the radial component of acceleration of b dash. And here is the point of intersection, that is b dash. If we observe this space diagram, then point Q is on the P dash extended. So here this is the total acceleration if we join the end points of this radial component and tangential component of b dash p. Then here with the help of black marker, this p dash b double dash indicates us the total acceleration of this link of p dash. Now we have to extend, that is in the same direction we have to extend this line, and on that line there is the point Q. So how to calculate? So we will take the ratio from the space diagram, that is p dash divided by b dash q. So we will take here from the acceleration diagram, which is equal to p dash b double dash divided by b double dash q dash. So if we observe this p dash we can measure, and it is 250. Then p dash q, it is 125, which is equal to p dash b double dash. So if we measure, it is 17 centimeter divided by b double dash q dash. So here there is only one unknown term, and which is equal to 8.5 centimeter. So from this b double dash we have to plot here the point q dash at a distance of 8.5 centimeter. Now this point Q is again attached to the link Q1. So again if we observe, there is the radial component of link RQ. So how to plot the radial component? So it is in the parallel direction to this link QR, and the direction is towards the center. So in this Q and R, the direction is towards the Q. So from this Q dash we will take one line parallel to this QR, and the direction we have to take towards the Q, that is towards the right hand side. So what is the scale? That is 0.5 centimeter. So I will take here one line, that is the 0.5 centimeter. So it is very small distance, and this point is nothing but we will say Z, because it is the component, it is not the total acceleration. We will show arrow also, and it will indicate the radial component, that is a raised to r rq. This will indicate the radial component. Now what about the tangential component? So it is perpendicular to this link. So I will take this line of velocity is also in the perpendicular direction. So from this point Z, draw here one perpendicular line, and it will indicate us the tangential component, that is a raised to t rq. Now how to locate the point R? So if we observe, this point R is having reciprocating motion along the horizontal line, and this motion is with respect to the fixed point. So from this fixed point, draw here one horizontal line. And this is the point of intersection, and this point of intersection is nothing but the R dash. So here the initial point is P dash and final point is R dash, and it will indicate us the acceleration of this ram R with respect to fixed point. Now Now we will move for the first question, that is the acceleration at point R. So acceleration at point R, that means we will measure this vector A dash R dash, because this R is having reciprocating motion along the horizontal line with respect to fixed point. So here A dash is the fixed point and this is the horizontal line that I have located. So which is equal to 24.5 centimeter. So according to scale, 1 meter per second square is equal to 1 centimeter. So which is equal to 24.5 meter per second square. Now we will move to the second question, that is the acceleration of sliding block B along PQ. So if we observe this diagram, this sliding block B or sliding block at point B is having coincident point B dash on the link PQ. So how we can measure its acceleration? So we have to measure the acceleration of point B with respect to B dash. So here it is indicated with this total acceleration, that is I have shown with the help of black marker, that is B double dash to B dash. So we have to measure this vector B double dash to B dash, and which is equal to 17 centimeter, and it is equal to 17 meter per second square.